The goal of this presentation is just to go towards LSTMs, but by going to this topic and not seeing the basics would be just a bit complicated. So I'm going to trace this whole path from the building block of artificial neural networks, and then we can go like higher level and talk about LSTMs and applications, okay? So just one or two slides about artificial intelligence just to get a context. Then we can go like get a context on machine learning, and then we just start from the building block to the to LSTMs. Okay, just feel free to interrupt me and ask a question. So yeah. So about artificial intelligence, this is a famous field right now. Let's just stick to a bit skeptical definition, not about mimicking human organic process, nothing about that. Just let's stick to math. Some people, math and computer science. Some people say artificial intelligence. I would rather stick to computational intelligence. The term artificial is just like something with respect to the human ability. So yeah, both terms are interchangeably. So
I'll let you go, but if you write artificial intelligence, never heard the word computational intelligence, so there is no track record there.
Okay.
So it's fine, but I would like to say, if you're going to say something,
use AI.
AI. Okay, that's the main recommendation.
Yeah. So machine learning, LSTMs, neural nets, it's a subfield of the AI field. So, and this field, we have several other subfields that uses machine learning. So yeah, lots and lots of subfields, including classical, like search, like other strategies of AI, classical AI. But we're just going in this branch of this whole field, okay? So for now, let's just stick to this definition, the ability to perform learning. Learning really as learning, not committing to memory, just learning. We have context. You like generalize, this is an important word, generalize. So we can like perceive what's going on and like detect patterns, predict something, get the whole idea of a context of applications. Yeah. So one more time, generalization is a core concept to take into account when we do machine learning, when we do data science. From statistical learning theory, this is a whole other topic. I'm not gonna go through this today, but the statistical learning theory is the field that provides the whole background, the whole foundation of why machine learning algorithms work. Why do they work, right? So yeah, this is an important thing, and let's just stick to generalization. So we have data, we feed it to some mechanism, and so this data can be seen as previous experiences. So we have an experience, from that I learned that this pattern, this data should be like this class, this, I see the data in a specific way according to what I learned before. Pretty straightforward. So yeah, there's this good saying from Edwards, Deming, in God we trust, all others must bring data. And this is just a silly thing about generalization. So your data must be representative. You just don't pick a sample that you put whatever you want to put. It must be representative. So yeah, you're training a model expecting that it would like classify something correctly according to poor sampling. So you have a few of what you're gonna test, and some people say it doesn't work. Blame the mechanism, blame the architecture. So yeah, representativeness is also important. Study the data, look at the data, and see and know what data you're dealing with. Okay. So why do we use it anyway, right? Traditionally, we would just define rules let's just take this example of like color classification, like giving labels, what is red, like as a name, not as a shade. So we could have like a program, you get an RGB, and you define thresholds for each variable and say, oh, yeah, okay, this is red, this is green, this is blue. But what about a broader spectrum, I would say? What about other shades? So we wouldn't explicitly define thresholds if we have an RGB space. How can we define coordinates and stuff so really explicitly? So we better use something that optimizes and plays like hyperplanes. We can still define rules, but in a non-explicit way. And then we can use this model to classify. So we must have a representative sample, we train it, and we use it, okay? So that is the main difference. This is a motivation to use machine learning mechanisms. So we have lots of like modalities. I don't know that this is a word, but we have supervised learning, which is what we're going through today, which is like when we have labels. I have this input, I expect the model to output this. It won't, it will like get something close or not. We compare it, we optimize it until the error is loaded. So yeah, we have an expected output. This is why it's called supervised. We have a specialist in the area who will label. This is a human labor, okay? So the specialist in a context of application will label things, label points, examples, and then we feed it to a mechanism to learn. So classification would be just like something categorical. So in the color classification example, could be like, I give them these values, which class it is. Is it red? Is it green? Is it brown? Something really categorical. Regression, we can go a bit, if we have time, through this. Regression would be just a continuous output, like fitting a curve. So yeah, it's pretty straightforward. Unsupervised learning is more of an investigative way to do it, for like perceiving gatherings of points in space, like clustering, find groups. So you don't really know how many groups there will be, but once you find them, you can like label these groups and then just jump back to this. So groups can become labels. It's just an investigative way to approach a problem, okay? And semi-supervised, which uses both approaches. So yeah, we're just going this way today. So we all say, oh, well, let's use a neural net, but this is not only, this is not all, this is not machine learning. There are several other mechanisms. We have a decision tree here, for example. And let's give the same problem to two mechanisms. They have different search bias. So let's say the task here is just to classify points, okay? So we give the same problem to both mechanisms, but they will function differently, okay? While this one gives like rules like thresholds to each variable, it's always perpendicular to the hyperplane. Neural nets just go like positioning, placing hyperplanes freely on space. Okay, so it's a different bias, a different way to search in space, ways to separate data. So let me say it again, it is important to look at the data, which hyperplane, which way is best to separate data, and always towards the model as less complex as possible, okay? So what is the dynamics of using it? What is training, what is using? So yeah, we have a data set, like we need a model. So we feed it to a training algorithm of a neural network, for example. You feed it here, and yeah, the algorithm is gonna output your model. Yeah, here's your model. What is your model? What is a model? It's just a set of parameters, like weights. We're gonna look at ahead. And having this model, it's ready to operate. you have new examples in a context, and this is important. These examples were not seen in training, and that's when generalization takes place. So I learned from this, so I should know what this is. I should give the proper class. We have the input, the expected output. I have this input, I should infer correctly the expected output. So yeah, I have a model, now it's ready to operate, and we're using the application context, okay? Moving on, so let's go to the building block of a neural net. And let's just not stick to terminology yet. Let's just get to the simple math. And there are several building blocks which would go towards different directions of neural nets. The linear bias, the linear classifier would be the well-studied, the well-known, the well-explored in literature. But we also have radial basis function, which is another building block, another way to classify data in space, for example. But it would just go towards a different direction. So since our goal here is going towards LSTMs, so yeah, let's stick to its building block. So yeah, let's consider a line described by this equation here. Yeah, a simple line. We could rewrite it like this way, considering weights, even if we consider it weight 1, we could do it in this form and then solve for x2. And now we have weights, and then in this case 0.5 for x1 and -1 for x2. We can use this to get to the core operation of a neuron, artificial neuron, which is a dot product. So with these values of the weight vector, we can represent the hyperplane. Okay, we could describe the hyperplane. So we could use this to make projections of points, right? So there are several different interpretations of a dot product. Let's just stick to at what extent both vectors point at the same direction or opposite direction, okay? And let's just stick to the signal of it. So yeah, here is better. Given a point, and suppose our model is trained, let's make the dot product. If the signal is positive, yeah, we are on this side of the line. If it's negative, they point to opposite directions, it's in the other side. Just look at the signal, you're gonna get your classification, right? Pretty straightforward. So in this case, yeah, we have a positive, the class positive, the class negative. And so every point in the same direction of the weight vector would be one class and the opposite other class. And when the dot product is 0, vectors point to a completely different direction. So it's orthogonal. Since we're dealing with computer implementations, there will be numerical error, so it's really unlikely to have 0, 0, 0, 0, okay? So yeah, one class or another. Okay, questions? Okay, moving on. So far, the hyperplane is stuck in the origin, right? And sometimes the placement, the arrangement of points in space will not be, we can even center the data, but even so, we could be able to have this line to move freely on space. And that's when the bias term takes place, which is just the y-interception of a line equation. So if we have this dot product, we just add the bias term. So yeah, we can just adjust the slope of the curve and the y-interception so I can move it freely on space. For example, this, I could have centered, subjective mean, but in another specific arrangement, I could need to get out of the origin, all right? So this is a representation of the calculations of the dot product of a line equation, okay? And I just use, I'm just showing the natural one. Anyway, it's just common in the literature. I'm not a neuroscientist, a biologist, or anything like that. So yeah, it's kind of cute, but let's just stick to this model, which was proposed by McCulloch and Pitts. I don't know who's who, but one of them was a biologist, and the other was a mathematician. So they came up with this model. So we have our input vector in a d-dimensional space, and we have our weights, just like we have here. Each input is weighted, and then we sum everything together. We add our y-interception, our bias, and we can use an activation function, which I'm gonna talk in the next slides. You can either squash a signal, saturate it, or just look at the signal. So yeah, let's just take a look. So we have the model, but so far we are assuming we have the weights. It is functional, it's trained. But how can we get these weights, right? How can each arrangement of data needs a specific set of parameters properly adjusted. So that's when the training algorithm takes place, which was proposed by Rosenblatt in 1958. Okay, it consists of iterations to look at the data and set the difference. We need a cost function, like to measure error. Okay, and it's for this algorithm, it's a gradient-ish optimization, and I'm just going to explain you why. So you begin with weights randomly, all right? So you need a cost function. Let's say it's a squared error function, and we're going to differentiate it with respect to the weights. We're going to just optimize this cost function using gradient, but if we use the signal function, which is right here, it's there's this discontinuity, so we couldn't differentiate it entirely, this domain. So that's when the gradient-ish takes place, because if we're gonna differentiate like f of g of x would be like the derivative of f with respect to everything is plugged inside times what is inside. So f would be this. So how could we differentiate this? So it was just considered as 1, and we differentiate what was plugged inside. And going through all the math, we could get to the equation proposed by Rosenblatt. Okay, so we could use like a sigmoid with like a steep. We can adjust this parameter, have like a steep, almost like a step function, like a signal function, which is differentiable. And this goes to the another neural network architecture, which is called Adaline, and so on. The guy who proposed to use this is still alive, and yeah. Anyway.
Is it?
Yeah.
Who proposed
I don't remember his name. It was Woodrow and Hoff. Woodrow is his last name, but I can't remember.
So keep going.
Anyway. So yeah, we can separate points in space, but we must assume data are linearly separable, right? We have a line, so we must expect a linear way to separate things. What about the Exclusiveor problem, right? Just try to place a line in here and classify points. Everything should be classified correctly. There's just no way. Right? This is the Exclusiveor, like for logic. So points are not linearly separable. But what we could do is like combine this kind of model. We could use, if we consider each one of those as a line, we could use 2. Okay? So we could combine them, which was the motivation to build a nonlinear model. Because we could perform like an AND operation. If the point is above this line and below this line, we can say it's one class. Otherwise, it's another class. So what about this AND operation? AND operation just one point will be true. The rest would be false. So with one hyperplane, I could do an AND operation. So if I use layers, if I combine things, if I chain outputs, right? We could, oh, it's up here and down here. This is the AND. Okay, I use this to go to another to another space. I make a spatial transformation so that in that space I can do an AND operation with a line. So I make features more like abstract. This is the motivation to this architecture, which is a combination of perceptrons, which is the multi-layer perceptron, MLP. Well, it's not quite clear who came up with it, but the most famous name was Supervised in '74. And this uses like differentiable activation functions at each neuron. We can do really gradient optimization, not towards a maximum, but towards a minimum, okay? So that's why we call it gradient descent. There are variations, several variations. There's this nice approach if you deal with a huge data set, and if it's just unfeasible to go at each iteration to adjust parameters through all the data, we just pick a sample of them, assuming the whole data set is distributed from a single unknown probability distribution function. Otherwise, if we know the function, what is the point of using it, right? So if data have the same distribution, yeah, just pick some of them at each iteration and train, right? So we have layers. This is the power. That's when the power of this mechanism takes place, because it has layers. If we have one weight vector per neuron, we can see, for example, if I feed everything here, we have a dot product here. If I feed everything here, we have a dot product here. So we have a matrix multiplication. We have dot products with several vectors, we have a matrix, and we can think of that as a spatial transformation. So here, the dimension of the space is D. If we do this matrix multiplication, we're gonna output N1 values, which could be larger or lower than D, or less than D, right? So we go to a space with more dimensions. We don't know this, just don't know what's going on here. It's just a way to extract features in an abstract fashion, okay? And we just keep going on. So remember in the XOR problem, this was difficult for one hyperplane to separate data. But I used two, and the output here will allow me to use just one. I don't know what's going on here, but it just transforms the space. So it becomes easier in the next layer to chain this output to a simpler operation. So it goes more and more and more abstract as we go deeper, okay? So we have lots of hyperparameters. We have parameters, which is the weights, what would make the model useful. And we have hyperparameters, which are the parameters of the training algorithm, okay? So there's this difference. So since we're minimizing using the gradient descent approach, we have the gradient, and we can use the learning rate as the size of the step. Sometimes the gradient could be too large. So if we're minimizing, but the gradient is too large, we can just take a space, just take a large step, and you just pass the minimum, and you just go back and you pass again because the step is too large. So that's when the learning rate takes place. If we track the minimization at each iteration, which is called an epoch. An epoch is just every time you pass through all the data to adjust, it's an epoch. And then you calculate like the mean value of a cost function, for example. So we can if we do a large step, for example, we could just minimize, but sometimes we could just pass and the error goes up again. Oh, I passed, I must come back. So yeah, during the training, there can happen things like that, and you just go minimizing until a precision, so we're talking about error, so we can go until an error is low enough, okay? Another stopping criteria this is one criteria. Another stopping criteria could be the number of epochs. Let's go just to 3,000 iteration. Okay. So yeah, just feel free to use the way you want. Momentum rate. This is just another way to accelerate this convergence. Okay. Regularization is another way to like penalize the gradient, so the weights, the free parameters of the model are not too big. And there are many other variants in the algorithms. There's the optimization using the Levenberg-McQuartz method, which deals with Jacobian matrices, I guess. There's resilient propagation, and with this hype of AI neural nets, there are several other alternatives. So yeah, what are we optimizing? So cost functions. Which one should I choose? I don't know. There are many. You can look at the data. You could test lots of them. For example, squared error is one cost function. Cross entropy is another cost function. As a mathematical convenience, you could like optimize, differentiate this, and as a convenience, you could choose an activation function that goes like that won't give you a lot of trouble to differentiate. So you combine activation functions, cost functions, and so on. Okay. So yeah, let's go to a bit of practice. I developed this tool just to teach about it. If you want to just go to this link, we can go this together if you want. If not, I can do it, of course. So if we open the browser, if you hit just like MLP, which stands for multi-layer perceptron, .training, it goes to that tool. So let's use this as a way to discover how many layers should I use? Like how many neurons per layer? So yeah, let's use this tool to see the role of each layer, the functional role of each layer. So we have this data set. This is one class. This is another class. So we're going to classify them. So if we go to the link here, moretti.cb.com/layers.csv. We just have this data set, okay? I have it already. It's right here. Okay, so we have two inputs, one output. Points of class 1, points of class 0. Okay. Let's feed it here. So I already know I could use 3 here, 2 here, and 1 here. So 2 hidden layers, 1 output layer with these parameters. But I'll just explain why. But we can see it in practice. So learning rate. So yeah, we have 2 inputs, 3, 2, and 1 output. So we're using the sigmoid activation function, which is differentiable, goes from 0 to 1, okay, at each layer. So let's go here and provide the data set. The learning rate is 0.5 and the precision. All right, update parameters. We can visualize it. Let me just change the aspect ratio. Okay, just like in the slides, the background is just blue, which is just one class. The background is the output of the model. So it's randomly initialized, so we don't see any separation. But yeah, let's train. Let's see what happens. I hope it doesn't fail. So around 2,000 epochs, it's gonna classify well. Yeah, it's just starting. And we can see in the training tab, our cost function, like it's minimizing, look. Oh, it did it. All right, so it will end when the error is low enough with respect to our stopping criteria. So yeah, it went less than our precision, it stopped. I could use an epoch, could set a very low error, and I just check here. Oh yeah, okay, that's enough, I thought. So let's just take a look at the role of each neuron. So this is just a representation. If I type data in here, it could just output. This is a model ready to operate even here. But anyway, let's just plot everything. We have like, let's see the output of each neuron. Oh, it makes sense. What do we do in the first layer, like in the XOR example? We just place lines. This is a dot product just squashed by a sigmoid function. So this would be like this. The third dimension is color. Okay. So yeah, one separation here makes sense. We must expect, since we're talking about lines, another separation here and another separation here. Oh, 3 lines, 3 neurons. That's what we have. That's what we have here, 3 neurons. Okay. So yeah, let's take a look at the others. It cannot be another thing. Yeah, another separation. Another separation. Okay. So the role of the first neuron is like account for hyperplanes. Each neuron divided into space. Okay. What is the role of the second layer? What are these neurons doing? Let's check it out. Oh, yeah, this is curious. Let's just take a look in the this dense part. The role of the second layer is to combine hyperplanes to make convex regions. So this is just a result of the combination of 3 hyperplanes. We would need just 2, but that's why we have like spots in here. But let's stick to this concentration. Okay, if we see the other one, we should expect another convex region this side, right? Let's take a look. All right, most dense part is here. So the hidden layer accounts for convex regions. We have one neuron accounting for a convex region. So yeah, spoiler alert, the third layer combines convex regions. We just saw the training taking place. So mechanically, they're doing the same thing. I'm receiving something, I'm placing a line in a space, okay? I'm receiving something, I'm placing a line in a space. The same thing here. So why it's doing like this? It's doing this complex stuff. These roles we can interpret with respect to our input space. The semantics is here of our context, of our application context. This is the semantics. So from this space, I don't care what's going on here, but and in terms of what this dimension of this space represents, I don't care. I care about this. So optimization just go, if you chain these spatial transformations, you're going to end up doing complex stuff, more abstract stuff. Yeah.
Sorry, okay. About the first layer, I can understand.
The first layer.
The reason why there are 3 dots. But about the second layer, how did you decide the number of dots? Number of new.
Okay. So if we consider like 3 divisions here, 3 sections, how can we combine these 3? So the second layer accounts for convex regions. Let's just combine here. What else could I do, right? Combine here, combine here. This is just the convex regions I see, right? I could just do one region here.
I think you could have as many neurons as you want.
Yes, of course.
This is, in many cases, you don't even get worried about this. You just go to the brute force. So there is MATLAB and the others would kind of optimize. They are, I don't know if you are going to talk about how Bob Senna would decide how many neural networks
Oh,
you have.
no, it's not.
So there are a few methods where you might say, what's the precision that you want? And based on that, you define how many neurons you are going to put into your system. So most of the systems, it's kind of brute force. You start with a very large number, and then you start like creating these very simple rules that say, like you were saying, oh, how do you define the size of your learning rate? So you start one way, you start seeing that you are bouncing from one side to the other, you have the size of your learning rate, so then you can try to go faster. So those are heuristic rules. They are heuristic, and the same thing here. You don't need to be thinking in advance what is your problem. You just put enough layers, and you can perform if in principle you don't even need to have the second hidden layer. You could have only everything a single hidden layer and not two of them. Depends already. Here, this is already a little massage to have two hidden layers.
It would be like redundant if you add like, it would be an overkill, but essentially these roles would be just like the minimum choice of neurons, like a compact thing. But I'm not gonna talk about complexity because as you increase the number of layers, it gets more complex than just adding here.
So normally you just add them, and then the programs would find heuristic rules to solve it. And as far as I know, but this is a long time ago that I pay attention to that, I only saw one convincing way for you to define what is the spacing and how many neural networks you need, based on the idea of sampling theory. So Bob Sander said if you want to sample, you want the error to be below something, he defines the sampling, and then he's able to determine the precision, and then you run until you hit that precision. But most
in
of
this
them,
case would change the bias. It's a linear bias here, so we have the radio basis, which is interesting. The radio basis would just not separate data linearly. One neuron, I could use a radial basis function. It's a different way to explore the data space. So that's what Dr. Krebs was saying. We could get out with this layer, but not with the linear bias, but with the radial basis bias. We could just use radial basis functions here. Okay.
Okay.
So just for the sake of covering, it's taking a lot of time, so keep moving.
Okay, yeah, sure.
Because otherwise,
How much time do I have?
you have an hour and 10 minutes left.
Oh, yeah, I have a lot of contents here. Okay, so is there a specific function for each layer? Yeah, we just discussed about it. There's this universal approximation theorem proposed by Sybenko that says with enough number of neurons in a single hidden layer, and you have an output layer, you could approximate any function you want. It is true, it is. It is true. I just wouldn't do that, and I'm gonna show you why. It's based on bumps. So if you have a sigmoid function, you have if you plug in a sigmoid function a large value, you could just get this function to get steeper and steeper and steeper until being like a step function. So the beginning of a bump. So you use, so you can control this. What about displacement? We can just use the ratio between these values. So it's considering controlling this from 0 to 1. The weight could be, the bias term could be like 70% of the weight of this steepness. And yeah, we just place it at 0.7. So we control this ratio to place the beginning of the bump anywhere I want, okay? So I could keep the ratio and have lower values. It would just get more like this, but I can still place the center of the function anywhere I want. We do this, we did the same with the end. So yeah, the green one is the beginning of the bump. This is the end of the bump. So yeah, we can define the beginning and the end. So, but it's not a bump. It's two overlapping functions. So how can I do a bump? So we first sum the two curves, and then this one, the end of the bump, I just flip. I just multiply by -1. So each pair of neurons accounts for a bump. So I have the weight 1, I just keep the first function, I multiply the other function by -1 and sum it together. Okay, so we have a bump. So we could control the height of the bump. It's just about the magnitude of these weights. Okay, so if I want to place it at 0.5, so plus 0.5 minus 0.5. So each pair of neurons in the hidden layer accounts for the bump, and the output layer just aggregates everything. So yeah, we could like use 6 bumps to approximate a sine function poorly, and as we go on, we can use 12, and on the limit, I mean, this is ugly, right? Because, and I'm just gonna tell why it's ugly. Because we have 192, so a pair for a bump, I have 96 bumps, so twice as it. 192 neurons for bumps, approximating with bumps, and it's not smooth at all. Whereas we can use 2 neurons combining sigmoid functions to have a smooth approximation. I'm just going to show it quickly. So I have 1 input. I have, let me just erase that. I have 2 neurons here. So since I'm dealing with regression, I'm not squashing the function. I'm just using the magnitude of this dot product. If it's far or if it's near, I'm just gonna not squash by an activation function to do regression. So on training, this is a cool feature. You use a sine function here and it makes a data set. So yeah, precision 0.1 and learning rate 0.1 and the precision. Yeah, let's just check it out. Oops, did I do something wrong? No, I didn't. So yeah, right. 2 neurons.
So while I was doing this, Cybenko was very important because it guarantees that you can find a solution. So while this might be true that there are better ways to get it, and then you can guarantee that it's regularization, smoothness, things like that. In practice, I don't care if there is 192. I could have 384, 1,000, 2,000 if the computer is fast enough. So I understand the value of having things that are a little more elegant, but also on a practical side, and maybe here comes the difference between being a mathematician and being an engineer. If I have things that run fast enough, I'm less worried about having very large number of bumps, provided I know that I'm going to get the answer. So Cybenko theorem was very important because it guaranteed, it guaranteed that you can get the answer.
This could be even you don't even need training for that. You can do this manually by setting all the weights, right? I'll just defend this point. But,
you don't need to defend it. I think it's
I mean,
elegant.
A motivation would be from statistical learning theory. In this field, we could provide even probabilistic, but you can increase this probability. And if you follow the premises from statistical learning theory, you can provide guarantees of learning. So it's not learning by a coincidence. So this was proposed by Professor Vopnik, which works at Facebook today. And if you have as less as possible neurons, the model is as less complex as possible, so it would require a sample size, for example, still big, still huge, but something doable if we keep simplicity. this would be just the way to do, like, if you need to provide learning guarantees. Otherwise, if it just works for you, for your, if the precision is enough, if the functioning is enough, if the situations of your application context is enough, yeah, just use it. No worries about everything, just elegant. Okay? So I have some examples here. I definitely won't have time to go through all of them. This is a color sensor, as we talked in the beginning, a project I did in 2013, just worth checking out. So then just access this link. We have one example here. This is really good. I had this idea and I was so naive, I thought it was original. They had this idea before I was even born, which is part of modulating speech. So you have like 5 neurons in the input. So the middle one is the current character in text. The 2 first inputs is 2 characters before, and these 2 inputs is 2 characters after. So okay, I have what's going on, and I have my current character. Here, I think 300 neurons, something like that, here inside. And as the output, the number of outputs would be the length of a phonetic alphabet. So words are composed of phonemes. So we have this phonetical alphabet. So if I say I see the letter F, I see some letters before, some letters after, and then the sound would be the letter F. This is the phoneme. It's not generating voice, not generating signals. It's just a phoneme, part of the modulation, voice modulation. So then character by character, you have an array of phonemes. Then you go to a pre-recorded phonemes or even a signal generator. So yeah, this is just cool. Just a way to generate phonemes. And this is the one I can show. I won't show all of them. This is really quick. In the beginning. Makes no sense, right?
I like to go to my grandmother's house because she gives us candy. Well, only there sometimes. Sometimes we sleep over a night there. There's just something I can't stand in my family. My baby, my stomach feels I can't ever get to sleep.
Just sounds like Microsoft Sam. I don't know if you remember that. The voice, the text-to-speech tool, the old one from Windows. So, yeah, pretty good applications, just worth it, check it out.
So before you move forward, so one of the areas that there is a lot of interest in artificial neural networks is like, let me give you an example. There is a lot of people making contracts, right? So if you are able to eliminate that, can you start to eliminate? So you go to big companies and they will have thousands of contracts. If you could, for example, use AI to try to automatize those contracts.
Yes.
So those are examples of things that never crossed my mind until I start listening to people where they can apply this. So the same here is about talk, but you have one below about optical character recognition. So you can use this approach in things that didn't cross my mind. I think one of the biggest areas that this would have in terms of impact, curiously enough, is in all the kind of bureaucratic work that we have in lots of big companies. So I think what you call white collar jobs, you know the difference between white collar jobs and blue collar jobs? It's an expression in English. So people that are working offices, they come with white shirts, and people that work in the factories, they put like an overcoat that is blue. A lot of these things is going to eliminate a lot of white collar jobs. So, for example, in law firms, there will be a lot of people, a lot of the work that young lawyers today are doing to look for cases and things like that. It will be done by this type of technology. So it's a kind of curious what is going to be affected the most. I don't think it's the manufacturing, it's actually the service industry would be.
Yeah. You could even like scan something, you have an image, you can recognize characters. Then you can use like LSTMs that addresses like time dependency, what was written back there in the time, in a large time length. So LSTMs can account for context in the time domain, but we can use like simpler mechanisms to digitalize. So we have now characters, real characters, not just a collection of pixels, okay? So yeah, lots of good chained applications, okay? So yeah, what if we consider time domain? We could still like use multi-layer perceptrons in the time domain. So we define a time window of size like k, and you walk with this window in your time domain. So you provide the first k, you can predict the next one. Then you can just discard the first one, begin with the second until k plus 1, still a window size k, and predict the next one. And we could do it so on and so on and so on. But yeah, there's a bottleneck, okay? And here's a motivation to other architectures. So this time window is static. So yeah, it can be like too static. You cannot customize it. So it does the job, but there are better ways to do it. Okay, that's when recurrent neural networks take place. Okay. This is just one step from multi-layer perceptrons.
So before you go again to recurrent neural networks, there is another way that you can go between the two, is that if you, in many things that we do in engineering, second order systems are the case. So if you would take the previous system and actually put the dynamics out of it and put it back as an input. So you make, if you, which is also very like good, before we go to recurrent neural networks, if you make assumptions that what you are dealing has a particular dynamical order, say it's a second order system, and Moises, correct me if I'm saying anything wrong, or Kyle, you can extract the dynamics outside of your neural network. So you take, say you have x and x dot, you make the output go out to the integrator that then comes back as an input. So you can extract the dynamical terms out and feed back in. And that also can deal with the problem. So even though recurrent neural networks are becoming much easier than were before, when I was a student, the way that we would do it was to cheat and make estimates saying, what is the dynamical order of my problem? And once I made estimates, I put enough dynamic elements outside of the static map and feedback in the static map, and it would work for a lot of stuff. Okay.
Cool.
So just to be aware that there is, so before you move to recurrent, which
of course.
It's the right way to go today because it got much easier. Just be aware that even with the static map, you could do something that he's telling you how it could be done if it was only static snapshots. You actually don't need to be doing the static. You just put the dynamic elements outside of the static map. but you have to guess the order of the system.
Okay.
Move
Moving on. So yeah, this is a way to move on. Recurrent neural networks. So I'm just gonna change the notation just so all of this I'm gonna represent as this because this will get bigger. Okay, so yeah, just for notation's sake, we have inputs and hidden states. So we can treat as inputs because of this recurrency. So we feed an input, we have its matrix from the inputs, and we have a hidden state, which feeds back, okay? So you're gonna have the same size to feed it back. So yeah, this is the same size as the hidden neurons, okay? And you can make this loop as many times as necessary for your application. And then when you think it's ready to output, just use this layer, okay? You just get a context here, and yeah, output it. Also, as many times as necessary for the context. So yeah, is it clear? The notation, input, hidden state with the recurrence. So output, okay? All right. Sorry?
The weights.
The weights are these.
Oh,
Just representing, so just like I have here, an input and the arrow, I'm just pondering this, but this is just like matrix-wise. This arrow would be all the weights from this input, okay? This is bold, this is a vector. This vector, okay? All right, so this would be, just considering this because, well, we consider the arrows. This, if we just don't point it to itself, if you just open it up, it will just look like this, okay? But they're all the same thing in different time steps, different recurrencies and time steps, okay? So for time t, I get the state from the previous state, okay? I combine it, I can output, or I can keep chaining this information over time, all right? So this is what recurrent neural networks look like, okay? So yeah, this is just like this, okay? Just again, notation-wise, it's just like this, okay? Just like this in the first example, so I just extended. Okay, and one important thing to point out here, weights are shared. This is the same as this. This is not another network. This is just the same. What I could just point here, but I'm just opening up like this. Okay, so every single weight is just like the same. The weights are shared, and that could be a problem. Okay, so but let's just talk about some applications before going into these problems, which is a motivation for LSTMs. Okay, so yes, now we can address time dependency, and this no longer goes along with the statistical learning theory premises to provide learning guarantees. So yeah, this is it's not related. You just can't go. It goes against the premises of statistical learning theory, but which is like having no time dependency.
So remind me, what is MLP?
Multi-layer perceptron.
Okay.
So it is based on multi-layer perceptrons, but you feed data back to the hidden layer, okay? So we can deal with time now. So yeah, we can do prediction of an audio signal, like voice modulation. Now I'm talking about signals, not the phoneme stuff. Medical data, ECG, EEG, and so on, electromyography, okay? Music, we could go like music theory-wise, for example, harmony, I create tension with a chord, how do I resolve that phrase, or and so on. We could go like chord-wise, which could be like word-wise in the text. We could go but note-wise, which would be like characters or like rhythm. We could decide higher or lower level. That depends on application. Okay, and I have good examples of this. So we could do like the text stuff, like natural language processing, at character and word level. Okay, we could like use stock market and so on. Lots of applications, but in theory, okay, I'm gonna just go with a simple example, and we're just gonna see why this is just theory. So yeah, we have lots of different uses. Like I said, output when it's necessary, and just keep accumulating context before outputting. So we have like cardinalities, like I believe I can say that way. So one-to-one, this is called a vanilla neural network, which is just an MLP, okay? No recurrency. So we have many-to-one, so I keep like adding stuff. That is just, that goes towards the example Dr. Krebs mentioned for like a document which is worth to pay attention to, a human to pay attention. Like a sentiment analysis, I see suspicious, a sensitive subject to a lawsuit, for example. So like you can just output true or false, just take a look or not. Or on Twitter, like there's a show, there's a festival going on, and we can just assess the impact. Is it positive, is it negative, what's going on, what people are saying. Sentiment analysis. You get a text, word, is it good or bad? Okay, one example. Many-to-many could be like character prediction. I get one thing, I get the next one. Just addressing like the time window thing. Also like this, machine translation. This is how Google translate the principle, of course. This is how it works, but using LSTMs, not recurrent neural networks. So yeah, you keep adding some stuff, you get the context. I mean, in language, in natural language, we need context to see what word I'm going to say next, given what was said before. Okay, so yeah, machine translation. So yeah, lots of you're free to do what you want, like this size or like this size, and so on. And you can even add depth. So if we look, well, the concept of multi-layer perceptrons are well grasped. So this is a hidden layer. If we imagine the structure, just add one more layer at that mechanism. So this is the notation. And then we have the output layer, okay? So we can add depth to these mechanisms. Let's go to a simple example, like predicting this sequence, hello. So we're gonna use this kind of cardinality. I don't know if this is a name, but anyway, let's just go with it. Many-to-many, many inputs and many outputs. So yeah, we have this vocabulary. This is our domain. We can use only these letters, and we represent it as like a one hot encoded character embedding. So if I want to represent like H, a letter, its specific index is 1, and the rest is all 0. The sparse vector. Okay. So this is the input. This vector. So x1 would be H, x2 would be E. Okay. So to predict the sequence, we input H. What we would expect, E. We input E in our training sequence. We input E. What we would expect, L, and so on, like this. So we input H. It's not a character. It's the sparse vector. Okay. So we feed it. We have some weights, and we can like output it. We could use like another activation function called softmax, which just calculates the probability. We could just use, like in this case, the maximum value, but which is wrong in this case, like initial state, let's say like this, of initial randomly initialized parameters. So yeah, we input it. So this would be the output. So we have the expected, which would be E after an H. In our training sequence, which is hello, okay? So we use a cost function like quadratic error, soft cross entropy cost function. Use a cost function and do the gradient minimization. So in multi-layer perceptrons, this minimization is called the backpropagation algorithm. This is just backpropagation through time, just a fancy name to address time dependency and a huge chain due to time steps. We're gonna just go through that. So yeah, it's pretty simple, right? You input something, expect something, and well, it's wrong. You wouldn't just make this, you wouldn't just feed the output. You're gonna feed your training sequence until it gets right, so you can keep predicting. For example, for a large sequence, you could predict what will be written next given context. This is just a toy, silly example character-wise, but you can use word-wise and or anything like that has a sequence you can predict the other values. There's just one good example by Andrei Karpathy, I guess. The training sequence they used is like lots and lots of dissertations, and the output was just another dissertation, like a theorem that makes no sense in LaTeX. It was just outputting some stuff. And if you look at the compiled LaTeX, if you look at the PDF, it looks just like an academic work, theorems, lemma, number one, and figure makes diagrams. It's really interesting. How can it get at least the pattern? We're not talking about general knowledge, but the pattern of a document. It just gets really well. Okay, but we're not just talking about this toy thing, but a huge sequence of characters. Okay, so yeah, an example: word-wise prediction. Clouds are in the sky. So we can associate this. We can use this to predict. So yeah, context matters. So we need time. Time is important to predict it. Okay? But what about this? I grew up in France. Blah, 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 half an hour speaking. I speak fluent French because we can remember this. Sometimes we just won't have attention. But suppose we do. Let's suppose we do have attention. And this is the right the terminology for that, attention, which is the ability to get something in a long time window and get everything that in between and use it to make an accurate prediction. So how is it for RNNs? Well, just believe me, for now we could go through the math later. This is not matrix-wise, this is element-wise differentiation towards every parameter of the neural network. So this is the adjustment of weights, the equation to adjust weights in training. So the problem is we use the chain rule, and since the weights are shared, we get the output and we feed it back, and we feed it back, and we feed it back in a large time window. So you can backpropagate, you must backpropagate using, if you're optimizing with gradient, you're differentiating. The chain rule is so big for each time step. So for hello, it's just 5 time steps. But what if we're talking about a signal, right? High sampling rate, lots of points in space. So from time 1 until the end, this is a lot. Imagine a chain rule so huge, and nothing can be too small or too big. Otherwise, it would just go to what we say here, a gradient vanishing or exploding. So if one of the terms in this huge chain is 0, you screw it up. Everything's multiplied together. Okay? So the gradient can just vanish quickly. Or if you multiply a value by something bigger than 1, you can just explode instead of just vanishing. So we have these problems, gradient vanishing and gradient exploding. There are some workarounds. One of them is the use of LSTMs, but so we have gradient vanishing. We could truncate time, but we will lose attention, like just to get it shorter. Not a good workaround, but it is a workaround, depends on the context. So we're gonna set a time window and look at the past events, not all the way through the first time event. We could use the ReLU function. For example, if we get the sigmoid or the tanh, which is just the same output as sigmoid, but varying from -1 to 1 instead of 0 to 1. I think we have it here. No. Anyway. And we have the ReLU, which is just, if the value is positive, go linearly. So if we differentiate something linearly, it goes just like 1. Okay? So we can vanish using these sigmoid-like functions, but using ReLU, it won't. But yeah, there's the negative part. It's not, there's no like a solid explanation for this. And also, there are better ways to do it, such as LSTMs. I'm just giving spoiler alert. Anyway, we have gradient exploding, and a workaround would be also truncate time, that it would be off the table, okay? Or clipping. If we explode too much, don't let it, we saturate it. Don't let it go more than that. Another workaround would be, and that's the interesting part, all of this for this part, is using gated cells, okay? It's just a way to think of a valve or a transistor. You control the flow of information. Oh, this information, I'm gonna close the valve. This is it, this is not gonna go. Or this information is important at this time t. Yeah, let's open the valve. Let this information go. I'm gonna go, I say, not let go, but propagate through the time steps, okay, in our network. So there, we decide what to forget, what to store, and what to output through time. So this gating is just a nice workaround what made LSTMs famous. We could use gated recurrent units, which is just another variant, another neural network, but we're gonna see long short-term memory. It's a short-term memory, but way longer than the power of recurrent neural networks. Okay, so yeah, I'm not changing notations, just like different, because these images were made by Christopher Olah, a brilliant guy that works in Google Brain. He just made these images. So yeah, if we unwrap this thing, we have just like this, right? We have the input, an activation function, the hidden layer, the output, the hidden state, okay? Just like we saw before. So this is an RNN and this is an LSTM. So these are gates, okay? So we're gonna go part by part. So the main feature, this core element of the LSTM is this like context thing, which is just like a pipeline that I'm gonna store something. Yeah, add to it. Let me just store it. This is a vector, okay? That goes through time. Yeah, let's store the do parts. What can I forget? So yeah, let's get these specific parts and ponder this. We're multiplying it, and that's when gates take place. Okay, we have something. Okay, so this is our valve. We have something to receive, and we just know how much we're gonna open or close. And we have the sigmoid here, right? So from 0 to 1. So if the output is 1, I'm gonna completely keep that information, not forget it. If it's 0, yeah, I'm gonna get this value times 0 is 0. I mean, I'm gonna add 0 later, so I'm gonna add nothing. So this is a gate. My valve of information. Okay? So the first one is the forget gate. So you have the input and the hidden state, and we feed it, and we can see how much of it I'm gonna forget. So I have the context, and I'm just gonna, what is in the context, I'm just gonna take it out by this much, okay? So it's like a basic neural net. We have inputs, this is just concatenation, just like I showed earlier, the architecture, some inputs and the hidden state, which are fed back, okay? So this is just a concatenation. This is a concatenation of the matrix of the inputs and the hidden states, okay? So yeah, we have this matrix multiplications, the bias, and an activation function, just as we saw before, okay? And we have the how much I'm gonna open or close this valve. This is the forget gate. And then we apply this to the context, we're gonna show it later. And we keep this value, okay? We store, we have at what extent we're gonna forget things. The next is the store gate. So I wanna get, given the input, time t, what's going on, I'm just gonna say, what am I gonna update? And by how much? Okay? So, what am I gonna update? I have this candidate new information. So, and we have this times, operation, aggregating these two things. So yeah, what am I gonna update? And by how much? Yeah, let's ponder this and then let's add to our pipeline. Okay? So again, pretty simple neural net to define what's coming in this time t, what's going on. Okay, let's update this, but let's just ponder, okay? And then we just sum. So before we sum, we just forget what we have to forget in the context. Yeah, what to store and by how much, we just store. And this is the interesting part. This is really interesting because this is element-wise application, no squashing functions here. And this is the core element which goes from time 1 to time t. Okay? So element-wise operations. This is just awesome for differentiation, and this is how LSTMs overcome gradient vanishing and exploding. All right? So output, what to output? I store it. I'm not necessarily gonna output everything I have now. For this time t, what is necessary to output at this time? Okay, we have the output gate. So I have my context. What am I gonna output? Okay, so another neural net. What to output? And by how much? And we just output here and here. Like the hidden state we have in the, as we see in recurrent neural nets. And if I just want to output at this time t, yeah, it is just the same thing. They're concatenating, I'm sorry, I just forgot to explain that. When arrows collapse, we're concatenating, as we see here. And when arrows split, it's just a copy. So we concat this, we define our gate, and here we just copy. We just go to the current hidden state, or we just can go towards another output layer, okay? And so on. So yeah, gates, we have what to do and by how much. To forget, to store, to output. So yeah, this is a good part. So as I said, it's a way to overcome vanishing or exploding gradients by this core element, the context, okay? So the differentiation here can go all the way through the first time step, okay? Just because of the simpler element-wise operations. So yeah, these are good examples. Do we have time? These are really good.
Yeah, we have a little time. Half an hour still.
Oh, cool. So this guy's so funny, and creative.
Sick.
This is an example of Bach. It's a MIDI file, and this is just, it's important to say that this is MIDI. MIDI is an interface to say that note is on, I press, and this velocity, that note is off. What is going on is like describing the music. It's not signal, it's not waveform, okay? So yeah. Anyway, we have an example of pieces of Bach, and he starts to train it. Yeah. 7 minutes. It's just rubbish, right? Using LSTMs.
So, looking at every 7 to 8 minute intervals. So here's 15.
So yeah, it makes no sense.
22.
22.
It's just a shut up. Take a chill pill. Anyway, let's see what it learns after 30 minutes.
Less of a noise, but still rubbish. Okay. More calm.
It's LSTM. And now 37.
It gets more pauses, like longer notes. Moving on.
Hey, I'm doing all the training on CPU, so once I get a GPU, this could speed up by orders
this
of
is true.
magnitude. Anyway, on to 45 minutes.
Anyway, let's just keep going.
Before I show you 52 minutes, I want to let you know that instrument has nothing
Yeah,
to do with
anyway.
the training. The network is never going to learn how to change the instrument, so you can pretty much ignore it. On to 52 minutes now.
52 minutes. Pretty much different from the rubbish in the initial 7 minutes of training, right? So let's just go to
Get this.
harmony. So yeah, it screws up, and
Which sometimes after
so afterwards he just the bias in sample was just Bach pieces, and then he started to put like Mozart, and so different ways to compose, different harmony stuff, and just enriched the sample. Let me see.
It requires the most memory.
Looks like a beginner, okay? It's getting to it.
But not much improved.
I want to show, yeah.
6 hours of training.
It kind of goes, but it goes on. Yeah, it learns these dramatic stuff. So yeah, lots of elements and music, like pauses, like harmonization, and so on. And it just takes time, but it gets there. Like several pieces and pieces and pieces of composers, and lots of training to get to harmony and stuff. This is also good.
84480
This is a training sequence.
81017 98827 80930 28722.
Now training starts on rubbish. And once you give time, you learn pauses now in the natural speech. Sometimes lots of pauses. Yeah. 0 0, you just learn like, it starts to learn things. 4, 9. So yeah. This is funny. 4, like 4. But it's just going towards learning more and more. Yeah, let's just go on. So much better, right? So still, it is necessary like to look at the sample, the bias and sampling of what you're doing. So it's not just throw some garbage and expect it to spit nuggets. Just not like that. Okay, it's important to keep track of everything you're doing. So let's see if right here. So it's a whole phrase. Makes more sense. This would be a good example to continue that example using MLPs to generate phonemes. Once you generate phonemes, you can like train to generate waveforms and so on, just one project to change to the other. And yeah, audio, a long sequence, even in a brief speech, you have lots of data points compared to our toy problem, the hello training sequence. So yeah, it deals with pretty much large time window, and this is just awesome. Google did some good work here. Let's go to some experiments. There's this one of drawing. Where is it? Oh, here it is. Predicting handwriting. This is good. I don't remember how to use it anyway. Oh yeah, we can see it. Like if you begin a letter, like a C, it will just predict the path of the rest. This is just amazing. Where can I? Oh yeah, a C, an A, an I, look, an O. It makes sense. I mean, it's not beautiful, but it kind of gets the direction I'm going. This is just amazing. Another experiment would be this. This is good. It's like a game. Draw basketball, less than 20 seconds. All right. My drawing skills are terrible.
Disco de hóquei. Mesa.
Oh, sorry, it's important.
Vejo caneca. Lata de tinta. Xícara.
Yeah, I'm lousy. Let's go to other example.
Cesto. Desculpe, não consegui adivinhar.
I'm sorry, I couldn't guess, but yeah, makes sense. I'm lousy. Tennis racket. Let's go to something simpler. Yeah, I think I can do that. It will look like an egg, like a spaceship.
Ou canoa. Ou cachorro quente. Já sei. É disco voador.
He guessed, and it was lousy. So it's good. I mean, this is an example of many to 1, for example. So many points in the sequence, I'm drawing, and this one output could be a sparse vector of several categories. So yeah, so sparse. So yeah, the spaceship would be that index is 1. Okay, so and that could be an example of many to 1 applications. Let's go to one more. Let's see.
Okay, so maybe instead of going to another one, maybe it would be good to. I'm guessing you are at the end, right?
Yes, yes. So yeah, so just some useful links. My tool, not because it's mine, because it's like good for learning multi-layer perceptrons. I based this presentation in like these three links. Very good stuff. Just worth to take a look too.
So
yeah,
I
thanks.
think that was very good overview.